Yeah. So we started off last time, did a little bit of math basics. We'll do a few more of those today. Make sure you guys see the stuff that you're going to need to know through the semester. You'll mostly learn these things through your discussion sections, right? Actually, before we get started, are there any business issues, any problems we're having? For one thing, I didn't mention explicitly last time where you get your textbook and your so that you probably all know this, right? Does anybody not? So first of all, does anybody not have Mastering Physics Access and don't know how to get it? All right, people may have it. Although you don't do short class, so maybe the people are wondering where I can't do it. Anyway, yeah. So if you're good with that, then I will continue. But yes, there's a workbook that comes with discussion sections that may or may not be used. Some GCSIs will use it, some won't. Depends on what section you're in and how they like to run their discussion section. But anyway, that all comes bundled: the textbook, the workbook, and the Mastering Physics. So we'll do a little math basics. We'll do some one-dimensional motion. And in particular, in this part of the class, we're really doing kinematics, which is a fancy way of saying that we're describing the motion of things, but we're not talking about the physical laws that underlie, or if you like, we're not looking at the causes of those motions, or the causes of the change in the motion of an object. We'll get to that when we get into forces, which is next week and the week after. We'll start talking about the causes, the physical laws that cause these things. So right now, we're talking about really just math, defining and describing different types of motion, right? So we'll do some one-dimensional motion. We'll concentrate on constant acceleration, which is a really important type of motion. That's not the only special form of motion we'll experience in this class, but it's the most important one, probably. And we'll do a little bit of an intro to 2D. Here we go. To 2D motion, all right? Okay, so to start off, we have our definitions for velocity and acceleration. We talked about velocity last time. There's lots of different kinds of velocity, though, right? There's instantaneous, there's average, meaning time average. There's also a notion of, well, here, let's define this and we'll get there. So instantaneous, what do I mean? I mean dx dt. You can think of this as a limit of the average, right? So I think you know this from your calculus class, but the limit as delta t goes to 0, right, of the average acceleration. So that's just x at times t minus x at times t equals 0, right? And then we divide by t minus t0. I'll just put it down like that. So we'll typically set t0 equal to 0 just to make our equation simpler. But sometimes you'll have problems where you'll have multiple times in the problem, and you'll sometimes use as your initial time some non-zero value. So just keep track of that. That's why I put explicitly in there to make it clear where this comes from. Take the limit where this, which is what I'm calling delta t, right? Delta t is my t minus t initial, or t minus 0 in our case, right? And our delta x, what's that? It's just x at t final minus x at t initial. So I've got lots of different symbols going on here. I've got final. Here I didn't label it. I just called t, so that your textbook will use t to mean the current value of time, or the value of time used in the equation, right? Sometimes I'll use an f for final. Sometimes I'll use an I for initial. Sometimes I'll get 0 for initial. Sometimes we'll just call it 0. So just there's lots of different notation flowing around, but those are the basic things you'll tend to see. Keep your wits about you. If it's unclear what I'm doing, raise your hand and I'll try to straighten it out. So this is just delta x over delta t. Take a limit when delta t goes to 0, and this just becomes the slope of the curve. Just to remind you of that again. If we draw x as a function of time, you'd say, oh yeah, we've got some curve. Well, the curve isn't necessarily straight, but if you look at a small enough part of the curve, it looks straight. As long as it's differentiable, it's a smooth enough curve. If you get to a small enough delta t from here to here, say, yeah, this little region of it is pretty straight. And you can ask how much did x change? Here's your delta x, here's your delta t. You let those things shrink down smaller and smaller, and then you wind up with, you can say, what is the slope of the line that's tangent to this curve at this moment in time? That's what I mean by the derivative of the curve, right? So there you have it, all calculus in a minute. Okay, that's our instantaneous velocity, and that's our average velocity. So we can write that down here. Average velocity, write average as a bar on top. Average velocity is just delta x over delta t. So if you think about that problem we did last time, little Jimmy's got to get to school, right? School is, how far did I say? I said, okay, school is, I think it was 2 kilometers away from his home. He's able to walk at a certain speed. So, well, how fast does he move? He moves at 1 kilometer per second, per hour. That wouldn't be very plausible, whereas 1 kilometer an hour. That sounds more reasonable. And we drew a picture of this. Let's say that he walked to school, and then realized he forgot his eraser. He's got to walk home. At least for me, pencil's nice. Eraser's crucial, right? I just have to go back home. So here I go. I walk to school. I walk back home. So when I draw, I label my axes. This is time, and this is position. This is a one-dimensional problem. So there's just x. Maybe I'll draw a picture of the situation. Oh yeah, here's home, right? Here's school, right? This is the x direction. We might as well on the x-axis label this here. These labels aren't supposed to mean how far they are on the x-axis. Let's change my labels. Let's put it up here, home, school, and then I'll refer to this as x equal to 0, and I'll call this x equal to d. It's a positive number. Okay, so now I know what I'm talking about. Now I go over here and say, sure, when I told in the problem description, I'm told how fast he's able to move. And I'll say, okay, that means that the slope of this line can either be positive or negative 1 kilometer an hour, right? So if this thing is right here, what did I say it was? It was d. Oh, sorry, no, confusing things, aren't I? D has to be on the x-axis. That's distance. So that's my d. All right. And then this could be, let's say time equal to 0 is the moment that he walks out of his door at home, right? Just to make our life easy. So now we're using t sub I or t sub 0 equals 0. This will get more complicated eventually, so bear with me. All right, so we got t here. And let's give this another name. Let's call this t when he gets to school. Let's call this t when he gets back home again, right? So now I've labeled 3 different times in the problem. Great. So if I ask what's the average velocity, what is the average velocity from the time he leaves home to the time he gets to school? From these things, what's his average velocity during that time? Well, how fast is he walking at this particular moment in time? 1 kilometer an hour at this particular moment. That's how fast he's walking the entire time, right? So if I took an average across all that, if I took an average across that whole time, right, I would get the same value every single moment in time. So this is a case where from here to here, his instantaneous velocity is the same thing as his average velocity. But we can also calculate it just using our formula, right? The average velocity is delta x over delta t. Say, delta x. Okay, so from here to here, the average velocity, I should be clear what I mean. There's a lot of different times here, so maybe I'll be clear and say, oh, from 0 to ts. So just during this first segment, what's his average velocity? Oh, well, that's easy. That's just delta x over delta t. So it'd be, if you like, x at time t. I'm really being pedantic, I know. Times 0 over ts minus 0. All right, what do I get? I get, let's see, this is, x at time 0, that is 0. X at time t, that's equal to t. And I divide by the total length of time, t sub s. There you have it. So there's his average velocity. If we solved all this stuff, solving all this stuff as we did last time, we found, yes, you divide one by the other. Just unit analysis tells you how much time has elapsed. The only way to combine a distance and a velocity to get a time is to divide the distance by the velocity. Because that cancels out the kilometers, and you're left with hours in the top. That doesn't tell you what the numerical constant is in the front. But anyway, so this problem is so simple that we can just figure out from unit analysis what the velocity has to be. It's just d over v. This is equal to d over v. I just calculated it explicitly for the average velocity, so we can just isolate for this. But anyway, when all the dust clears, what do we have? We have that the velocity is 2 kilometers an hour. No, 1 kilometer per hour. Okay, and it's a positive number. It's positive. You know that because in positive time, as we go forward in time, he moved in the positive direction on the x-axis. So the reason we got a positive number for his velocity here is because of the way we set up our axes. Some of the answers you're going to get in this class are going to depend. The signs of those answers will depend on how you choose your axes. right? If I chose to draw my positive x-axis that way, so that school is over here and home is over here, as I've drawn it, the positive x-axis that way, I get a negative answer for the velocity. That's okay. As long as I'm self-consistent with my definitions, that's fine. There are some things, though, whose sign is not going to depend on your choice of axes. And it's a good thing to keep track of that as you go through the class. Some things depend on your convention, some things don't. So the sign of the velocity, yeah, that depends on our conventions. Now the speed, if I ask you about the speed, right, is the absolute value of the velocity, right? So speed is always positive. So his speed is also 1 kilometer an hour. In fact, over here, his speed is also 1 kilometer an hour. But his velocity is negative over here, right? Because he's going in the negative x direction over time. So if I ask the question, what's his average velocity from time 0 to time th? So what's that going to be? Will it be positive or negative? Looking at this picture, what is his average velocity from here to here? 0. I agree. And there's several ways to see it. One is just to plug in the formula. If you stick in the stuff right here, you say, oh yeah, x at time h, t sub h minus x at, okay, these are the same. His x value is the same here as it is here, so you get 0 over whatever time it is, ts, excuse me, it's th, excuse me, th. But 0 over anything is equal to 0, as long as this thing's finite, and it is. It'd take an infinite amount of time to get back home, so we get 0. And I didn't bother to put my units down because 0 is 0 is 0. It wouldn't matter if I had kilometers an hour, kilometers per second, meters per second, doesn't matter. So whenever I get 0 for an answer, I tend not to worry about the units as much. I'm going to keep this visible, just keep moving my way down. Okay, so there's a pretty trivial problem, sort of going through it front to back. Acceleration. So what about its acceleration? Well, we can ask about, just like the velocity, we can worry about both average and instantaneous acceleration. Average acceleration is just going to be defined as, analogous to an average velocity, the change in the velocity over the change in time, right? Once again, we can take a limit where delta t goes to 0, and you can guess where I'm heading. Yes, you get instantaneous acceleration, and that's just, I'll just write dv dt. And we can write that also. We know how to write v in terms of x, so we can write this in terms of x, the second derivative of x with respect to time. Nobody's shocked, but anyway, good to see it all written out. So if you look at this case here, there's no acceleration going on along here, but there's a lot of acceleration happening right here where it turns on a dime, right? And so we can ask, what's his average acceleration during the time from 0 to th? So what would that be? Well, for this problem, I'd say, I'll just plug in up here. And again, I'll say, well, average from what time to what time? Let's go from 0 to th. Just so it's clear what I'm talking about. Is a subscript on this thing. Okay, so that's just going to be the change in the velocity. So what is the change in the velocity? His final velocity is positive or negative? Yeah, one person said it. Positive or negative? Negative. Someone agrees? Negative. And how do you know that? Because it's down slope. X is positive in the up direction, time's going that way. So as time advances, you're going negative directions. It's negative velocity. So it's velocity at time th, right, minus velocity at time 0. We divide by our delta t, which is just th, right? What is that? This thing is a negative number. This is a positive number. He starts off with a positive velocity, but we're subtracting it. So you subtract the positive numbers, it's a negative, right? We get two negatives. We wind up with 2 times his initial velocity, which was, what was it? It was 1 kilometer an hour, right? So it's negative 2 kilometers per hour per whatever th is. Oh yeah, that's going to be 2. It's going to be 4 hours, right? If we go through the math, 4 hours. Everyone agree? Anyway, just to make it clear what I mean by this average acceleration. So 2 over 4, it's a half. I can even do that in front of people watching me. The board, make a kilometer over hour squared. Good, so that's my acceleration. Does it have the right units? Yeah. So distance per time squared. It's negative. Does that make sense? Yeah, it does. Because he started off with a positive velocity, ended up with a negative velocity. Yes? So last time I accidentally stuck in 2 for the velocity, but I think I think this is the same stuff I used last time, and I got velocity is 1 kilometer an hour. So I think I want a 1. So that's why I try to take really careful notes so I can go back and figure out what the heck I was doing. There's going to be factors of 2 floating around all over the place, right? So I think I've got it right, because I've got 1 kilometer an hour is how fast, this is how fast you can walk. So in fact, the problem tried to tell me what speed was, didn't know which way he's going. It just said, oh, here's how fast you can walk, 1 kilometer an hour. So maybe I should have said, okay, let's call this his speed at any moment in time. Just to make it clear, that's just a magnitude. It doesn't say whether it's positive or negative. So I think both of these are 1 kilometer an hour. The only question is whether the sign is right. And I think this one's negative, it's the final time. This one's positive. So do you agree? Does that seem right to you? Keep me honest. Make sure my factors of 2 are in the right place. So I think that's right. But thanks for asking. I get a half out of that. And my units are kilometer per hour squared. Good, so my units are correct. I think it's plausible in terms of the magnitude. Yeah, that's about right. The thing is, this is kind of a funny problem because all the acceleration happens at this moment in time. As I've drawn it, it's instantaneous. The acceleration is infinite, huge at this moment in time. It's cusp. But if I say, what's his average acceleration from here to here, I divide by that full length of time, and it makes it a reasonable number. Anyway, all right, good. So that's the definition of average acceleration. Instantaneous is just you do the same thing, but it's a derivative instead of taking macroscopic, big finite differences, right? Okay, so given all that, oh yeah, my notes. Given all that, we can start asking questions about special types of motion and get a feeling for what kind of curves you get. I already mentioned that constant acceleration is a special type of motion, so let's think through what these curves would look like for constant acceleration. In this case, this is just constant velocity. We talked about speed here, velocity, instantaneous versus average. And now let's talk about constant acceleration. So I'm going to draw 9 different graphs here, and I'm going to make them for constant. So let's see, constant position, all right, and we'll do constant velocity, and then the most interesting case, constant acceleration. And I'm going to draw 3 graphs in each case, all of them with time on the horizontal axis. So I'm going to ask, okay, well, suppose we have position. Here, let's do it this way. Position as a function of time. All right? So what's that going to look like? See how much space I'm going to have. Let me give myself a little more room here. So position versus time. Well, if it's constant position, that means that it doesn't change. We talked about this last time. It falls on the counter, right? Pretty boring, but that's okay. I'll label this x naught to mean the initial position, but it never changes. So the equation is x equals x naught. Right? Pretty unsurprising. So we can also talk, in this case, about velocity, right? So what does velocity look like? Well, it's also constant, but what constant is it? What's the velocity for that ball? 0. Yeah, like half the time when I ask you a question, the answer is 0. But not always. All right, so there's 0 right here. Very good. Acceleration, what's it going to be? You bet, 0. If the velocity is always 0, it's not changing. Acceleration is how fast the velocity changes. The velocity, if you like. So that's also going to be 0. All right. Painfully simple. And these will all be pretty simple, but they're a little more interesting on the right side. So if we go over here now, see, all right, constant velocity. But before we do position, let's do velocity. There's a lot of different choices I can make here. I can choose different values. Let's just choose a positive value for the sake of argument. That's what it looks like. That's constant velocity. V equals V naught, right? Well, for x then, what does that look like? If V equals V naught and V naught is positive, I get a straight line here. It has a positive slope because V naught is positive, right? But I still have a choice about where I start off. I can start off in the negative, this is x, right? I can start off negative, positive. The v as a function of time curve doesn't tell me where x starts, right? But if the problem description says, okay, Jimmy started at home or whatever, and I decide to choose to make home 0, my origin for my x-axis, then I would start right here. But in general, I can start somewhere else. So I'll just put it right here to be general about it. And say, okay, he's got to go to the right, has to be a straight line, and the slope has to equal whatever v is from the other plot. So, okay, that's the kind of plot you get. But you can have, in general, they can be going up, going down, right? X naught can be positive or negative, whatever. All right. Now I go to acceleration, but acceleration's pretty boring, right? Because, well, what's the acceleration? 0, you got it. All right, so acceleration's like that. Okay, so now comes the interesting case, and I didn't give myself a lot of board room. I'm going to go ahead and push back my axes a little bit, give myself a little more room. So constant acceleration, let's start at the bottom. Constant acceleration then looks like this. It's a constant acceleration, it's just a horizontal line. Let's make it positive. So this is positive constant acceleration. I'm giving it an a naught, but we won't use a sub naughts very often in this class. And there's actually a sort of deep physics reason for this. Constant acceleration comes up a lot in physics because the laws of physics, it turns out, affect acceleration directly. When you write down Newton's second law, in whatever it is next week, the week after, that's going to relate, F equals ma, right? Well, A is acceleration. Acceleration is the thing that forces directly are affecting. In other words, we talk a lot about the first and second derivative with respect to time of position, but we don't talk about the derivative of the acceleration, which is called, I think it's called is it the jerk? And then there's the snap, right? There's actually snap and a crackle and a pop. It goes on and on. There's all these derivatives you can take, right? And why don't they show up in our equations? It just turns out, luck of the draw, that the physical universe we inhabit has laws that affect velocity sometimes and acceleration a lot of the time, but they don't really talk much about position and they don't talk much about higher order derivatives. It turns out. So it turns out these are special. Focusing on constant acceleration is really useful because it shows up a lot. So a lot of physical situations are like this. Like if I throw something in the air, right? And wind resistance, which affects mostly velocity. If you neglect wind resistance, the only force acting on this guy is gravity, and the result of that is that it accelerates with constant acceleration. What is the acceleration of gravity? Yeah, everyone knows that number, right? 9.8 meters per second squared. In this class, that's 10 meters per second squared. I don't care about the second digit, but I do care about 10 versus 1. You can't say 1 meter per second squared. It's 10 meters per second squared. So it comes up a lot. All right, so great, constant acceleration. So now if you draw this picture right here, again, we have to make a decision about where the velocity starts. Let's go ahead and say that because we give ourselves positive acceleration down here, let's just make it interesting, make the picture more interesting. We'll say that we've got 0 of velocity here, and we'll do this. We'll make that our axis, if you like, for velocity, and we'll start off down here. Here's our v naught. Okay, so if we do that, this is constant positive acceleration. So that means that we get a straight line curve here. I mean, it's exactly analogous to this being here, and then that's going to look like that. So we get the same kind of a plot, right? We get an upward straight line. Great, and it passes 0 someplace. So at some moment in time, velocity is going to equal to 0. Over here it's negative, over here it's positive. So if we draw equations for this, we'd say, oh, acceleration, well, we don't usually use a naught, but I'll just go ahead and write it that way. And then up here I'll say, okay, then velocity equals some initial velocity plus a times t. It's a really simple equation, really useful equation. Velocity is changing linearly with time, right? So if I have a piece of chalk, so we've already decided 10 meters per second squared, right? Gravity's pointing down, right? If I let go of this guy, he starts at rest, he speeds up. If I let the chalk drop for a second, how fast would it be going? Did everybody see how to get that from that equation? How fast is it going after 1 second? That was a mistake. It has to be longer than that. Now, one person's answering, but does everyone else see how to calculate it? I don't know. It's sort of surprisingly simple, right? It's just, yeah, the answer is right. It's 9.8 meters per second. Because every second, if the acceleration is 9.8 meters per second squared, that's a bit complicated, all these units. What does that mean? It means that every second, this thing's going faster by 9.8 meters per second. So after 1 second, it starts at rest, and I drop it. A second later, it's going 9.8 meters per second. I know it's riveting, but it's a good thing to know how to do. It'll save you time on calculations where you go and you look up your list of equations. Knowing how to use common sense like that for these equations is good. So that's good. 9.8 meters per second. Which, in other words, is 10 meters per second. Great. So if you draw our final picture, which is the most interesting one on the page, and you're going to take photographs and send it to your folks. Here it is. It's A versus T. All right. It's going to be not a straight line, finally. Thank you so much. That's what I'm looking for. That is fantastic. No, there were like 70 people out of their seats right there. No, that's good. Yeah, do not let me get away with it. Right? If I have, A or whatever I draw up here, that's good. Thank you. So now let's see what's going on. I want to have a curve that's going to go through 0. So I know that 0 right here means, what is the slope of the line going to be right here? It's going to be 0. It's going to be flat, right? Horizontal. But over here it's going to be steep. Well, steeper than it is here. Will it be positive or negative slope? Negative slope. So it's coming in like that. It's going flat. It's going up on the end. You guys know what that is. It's a parabola, right? Looks like that. And if I drew this, if I drew this correctly, so it corresponds with this. I didn't quite. I drew it over a little bit because I wasn't looking. I'll fudge it. Here's where it's supposed to be flat. So I'll have to. All right. We'll just cheat this curve a little bit. Okay. All right. So there's my parabola, smiling off to the side. And yeah, sure enough, velocity is equal to 0 here. He's going positive over here, as he must, right? And so if I integrate this, I can get the expression for a, right? I get my a equals a naught, right? That's my constant of integration. I get my v naught t. Oh, I didn't give myself a lot of room here, did I? Here, let's do that. All right, sorry. Board management. They don't teach you in grad school about board management. So you learn it only when the cameras come on. Here we go. All right, so it's a equals a naught plus v naught t plus 1/2, right? A t squared. That's what I got from integrating the t. I get a 2 that comes down. Oh, huh? Oh, yeah. Boy, I'm just a-centered today. I don't know why. Okay, x equals x naught plus v naught t plus 1/2 a t squared. Does everyone agree with that?